Hurricanes rank among the most dangerous storms on Earth. They inflict losses of billions of dollars each year. But hurricanes are agents of both destruction and rejuvenation. In the future, they may be more powerful and cause greater change than even those of today. Every year, the tropics stand in the path of the most powerful storms on the planet. In different areas, they go by different names. Typhoons in the Pacific, cyclones in Australia, and in the Atlantic, hurricanes. All are names for weather systems born from almost identical circumstances. All have the unique visual signature of a disc-like storm system, rotating around a calm eye of extremely low atmospheric pressure. With winds accelerating ever more viciously towards the center, all are potentially deadly. These unstoppable storms bear down on our planet with unimaginable intensity, affecting everything in their path. But these monsters have humble origins. Hurricanes are born on the African continent from harmless weather systems. Hurricanes are formed from weather disturbances that originate on the east coast of Africa, called African easterly waves. These weather patterns are associated with the West African monsoon, vital for countries such as Senegal, where almost 70% of the population is involved in farming. Dr. Aida Diongue Nyang is a meteorologist at the National Weather Center in Senegal.
There's an easterly wave that we've been following for several days that started at the east of the continent and which has moved to Senegal. And as it's moved, it has created convective systems that have caused precipitation in the Sahel and particularly in Senegal last night and this morning. Easterly waves, when they arrive at the Atlantic, can become what we call tropical depressions. A bit further from the coast, these tropical depressions can turn into cyclones.
Between May and November, these African easterly waves progress west across the Atlantic every few days.
Now, most of these systems that come off Africa do not become hurricanes. I would say somewhere on the order of 9 out of 10 do not. So you have to have a lot of things right for it to occur.
For a hurricane to be created, several conditions must be reunited. The first ingredient is warm, moist air over an ocean. The second condition is a warm ocean. Sea temperatures of 79.6 degrees Fahrenheit are the usual trigger point.
Without the ocean, there are no hurricanes that form over land. So you absolutely need an ocean, no question about it.
Air in the form of wind blows across the ocean from regions of high atmospheric pressure to low. As the tropical disturbance travels across the ocean, the winds evaporate heat and moisture from the seawater, creating fuel to produce powerful thunderstorms.
So as these thunderstorms move from east to west, they get larger in size. The systems that are going to develop will also have more storms over time joining them. So as you get this warming, you get pressures that reduce. And as the pressures start to reduce, you start to get the winds start to accelerate towards this incipient disturbance.
Wind rushes faster and faster towards the area of low pressure and growing thunderstorms, pumping hot air into the stratosphere. When the low pressure storm core and eye become sufficiently pronounced, the weather system starts to be influenced by planetary forces.
This area will grow in size, and it gets to a certain size, the rotational effects of the Earth starts to play. So you get this collection of thunderstorms starting to rotate.
If the disturbance looks set to become a hurricane that could threaten the United States, a team of elite pilots, known as hurricane hunters, are sent out to investigate. Pilots like Carl Newman fly directly into the storm.
Well, the principal role of air ops, or actually flying in the storm and the hurricane, is to actually get what they say is in situ measurements, or measurements in the storm itself, and we can report back to the National Hurricane Center what's actually occurring in real time in the storm itself, because satellites just can't see down through the clouds and the rain. You actually have to send an actual person in, and we do it here in this vehicle called a P3 Orion. Most of the time, the path that we take to the storm is the direct path. This plane is fast enough, strong enough, and can take pretty much anything, so that we want to be as precise as possible. We cut a straight path. We only deviate if we absolutely have to, and we do on occasion.
The hurricane hunters ride the hurricane for as long as their fuel load safely allows. The data they obtain helps to form a picture of the storm's state of health. Once the P3 Orions are in range of the hurricane, the NOAA hurricane hunters fly research patterns back and forth through the storm. Measuring atmospheric conditions within a hurricane is vital to determine if weather conditions are likely to cause the storm to intensify. For that, they need to put instruments into the storm itself. During the flight, they drop dozens of sensors into the hurricane. As they fall, each of them transmits weather data back to the aircraft. The data profiles help to locate the eye, the very center of the storm, where weather conditions are completely benign.
When they say hurricane hunter, what you're doing is you're hunting the eye by keeping the wind at your 90 degrees. So as the wind changes, you change the nose of the aircraft until you find the exact center of pressure, low pressure, and the lowest winds, which theoretically are 0.
Around this low-pressure center is the eye wall, a narrow band of intensely rotating thunderstorms that encircle the eye. It is this band around the eye that causes most damage when hurricanes hit land. And as storms cross the Atlantic, the entire Caribbean area braces itself for bad weather of varying intensity. Meteorologists measure hurricane strength using the Saffir-Simpson scale. A Category 1 hurricane has sustained winds of between 74 and 95 miles per hour, while a Category 5 has winds of over 157 miles per hour. The strongest recorded hurricane had sustained winds of over 190 miles per hour. Every year during hurricane season, Puerto Rico is hit by powerful waves formed by hurricanes. Even a small hurricane has the power to cause major damage.
If you want to understand the forces involved, picture this. 1 cubic yard of water is approximately 1 ton, similar to the weight of a small car. Well, imagine a wave containing dozens and dozens of cubic yards of water hurling at you about 20 miles an hour. The forces are certainly significant. Take that up to the next level. A hurricane generates waves in excess of 30, 40, 50 feet. We're talking literally thousands of the equivalent of small cars being hurled at you at 20 miles an hour. The impact is truly devastating.
Puerto Rico's offshore reefs take the brunt of these waves, absorbing 90% of their energy, while a mere 10% of their power arrives at the beaches of the city of San Juan. Over time, nature has evolved to cope with these annual onslaughts. In the remote Zapata swamps, the Cuban crocodile, the last representative of a reptile that evolved over 135 million years ago, has had to adapt to the annual hurricane season. One period of its life cycle is particularly vulnerable during this period, nesting season. Toby Ramos is the world's leading expert on the Cuban crocodile.
The biggest problem with the hurricanes is the raised water levels and the destruction of the vegetation. If that occurs during the reproductive season, the nest gets flooded. The chamber where the eggs are incubated fills with water so that it is impossible to get the gaseous exchange through the eggshell, and there is a high mortality rate. Here, our experience is that if a nest is flooded for more than an hour, the development stops, and there is no gaseous exchange. There is a lack of oxygen, so due to this, the embryo dies.
This nest is still in good health. With the mother keen to return, there's little time for the scientists to check her precious eggs.
The Zapata swamps are the last natural refuge where the Cuban crocodile lives in a wild state. There is shelter to protect them from the torment of hurricanes and winter storm winds. Here in the Zapata swamp, there is a hurricane roughly every 50 years. But during the last 20 or 30 years, we have had one every 4 years.
Cuban crocodiles have a life expectancy of over 100 years. Time enough for some of these babies to face as many as 25 hurricanes in their lifetime. Older, less vulnerable crocodiles have developed ways of coping with the hurricane season. storms begin, they seek shelter deep in the swamp. Fortunately, the Zapata swamps contain cenotes, limestone caves filled with water that provide a safe haven for crocodiles during hurricanes. Caves provide protection for a number of other species threatened by cyclones.
Most species of bats in the continent don't use caves as their main roost. However, when you come to the West Indies, most species of bats, they roost in caves.
Each year, the Caribbean is battered by hurricanes. Nobody knows where the next one will make landfall. The region's plants and animals have had to adopt a range of strategies for survival. While some manage to flee, other animals must find shelter somewhere. Hundreds of thousands of bats live in these caves in Puerto Rico. There are 13 types of bats, but they all fall into two categories. The first are the insect eaters. The other, bigger bats, are fruit eaters that take advantage of Puerto Rico's wealth of produce. The island also provides refuge during seasonal storms.
Living in a cave is an advantage because of the frequency of hurricanes passing through the islands. Caves are a safe place, and they will protect the bats from the wind, from the rain.
Protected by the caves, the storm itself has little effect on the bats, but the after effects can devastate populations.
So what we have observed is that insect-eating bats tend to increase in numbers after the hurricane. The fruit-eating bats, on the other hand, what they find when they come out is that many of the trees have been are devoid of fruits, of flowers. Many of the trees are not even theirs. When that happens, they will come out, and there will be no food for all of them. And that's when they face difficult times, and you will have high mortality of some of these species due to starvation more than to the hurricane itself.
In 1989, in Puerto Rico, Hurricane Hugo ravaged El Yunque tropical forest. Local rangers thought the forest was completely destroyed.
If you were sitting here 23 years ago, what you would see behind me would be great piles up of branches and leaves that were previously on the forest canopy. Hurricane Hugo, in 4 hours, deposited on the forest floor the litter, the debris that normally falls in a year. The scientists are trying to explain what are the mechanisms by which the forest recirculates the material that is dumped on the forest floor by the hurricane, and that's what we call the canopy trimming experiment.
Replicating the effects of a hurricane on a tiny scale requires a big chainsaw. It takes a full day to trim a single tree. Hurricanes can destroy entire forests in just a few hours.
The canopy trimming experiment was an effort by the scientists in Puerto Rico to understand what controls the decomposition of the debris piles that are formed after a hurricane. And in that experiment, basically what we did is that we cut the forest and dump on the forest floor the amount that we had observed after Hurricane Hugo, and then study how the organisms responsible for the decomposition, how quickly they operated, how quickly they decomposed the organic debris.
Normally, leaves and branches that age and fall to the forest floor are brown and poor in nitrogen. But a hurricane rips off fresh wood and lush green leaves packed with nitrogen. This fresh debris is a rich source of nutrients, fertilizer to the surviving trees, and resprouting undergrowth. With the canopy removed by the storm, sunlight is able to reach the forest floor.
We were in for a surprise because this forest regenerated so fast at rates that we never even imagined before the hurricane. The material was recycled naturally within 5 or 6 years because that's what hurricanes do. Hurricanes transport a lot of debris to the forest floor where it has to be processed before the forest can return again. So in this forest is where we learn a lesson about the resiliency of tropical forests.
While forests bounce back after a hurricane, humans survive by hunkering down, predicting where the storm will go and staying out of its way. Scientists are constantly at work trying to improve hurricane forecasts.
Hurricanes are part of nature. They occur. Some are not so severe, some are very severe. For us, it's an important geophysical phenomena that occurs in nature. We would like to understand them more, and by improving the understanding, we improve the models.
Hurricane forecasting models attempt to predict the weather and are central to NOAA's Hurricane Research Division.
How do these models work? Well, it's code, it's math, it's physics. The physics that's used in these models, though, make a lot of assumptions called parameterizations. A lot of parameterizations in there were developed decades ago. Guesses, if you will. Good guesses maybe in some cases, but guesses nonetheless. The end game is improving our ability to predict this phenomenon.
The very first hurricane weather forecast was made in Cuba in September 1875 by Jesuit priest and meteorologist Benito Viñez. He was the first to draw up a tropical cyclone warning, a long time before the arrival of satellites, radars, and all the other instruments we use to predict weather today. Dr. Jose Rubiera is a forecaster at the Cuban Meteorological Institute, founded by Fidel Castro after the disaster of Hurricane Flora in 1963. He is a well-known television personality in Cuba, where he has presented the weather forecast for the past 30 years.
Hurricane Flora was the first hurricane hitting Cuba after the revolution. It was in 1963. It was the second greatest natural catastrophe in Cuban history. Fidel Castro was very, very affected by the amount of casualties that Cuba had in this hurricane. It was a terrible hurricane.
Efectivamente, seguimos con más. La tormenta tropical Isaac continúa su paso por el Caribe insular. Y a esta hora nos vamos a comunicar con el doctor José Rubiera, el director del Centro de Pronósticos del Instituto de Meteorología de Cuba.
Bueno, aquí tenemos
The Cuban government depends on Rubiera's weather bulletins to put its hurricane protection plan into action. And the Cuban people listened reverently to his broadcasts.
La presión en el centro ha bajado a 992 hectopascal o milibares. Eso quiere decir que es
Our country, Cuba, has had a long understanding of hurricanes, mainly due to Dr. Rubiera's efforts. When a hurricane is close to making landfall, people are already evacuated.
Cuba is one of the safest places to be when a hurricane event makes landfall. The Cuban authorities are very concerned about what will happen to the people.
Accurate forecasting and state-organized evacuation have proven their worth.
In the last 17 years, we have seen 9 hurricanes stronger than Flora, and the loss of life have minimum.
But the storm-scarred buildings of Old Havana serve as a constant reminder that direct impacts from future hurricanes have the potential to be catastrophic. The cost of major storm landfalls can be staggering. In Honduras, in 1998, Hurricane Mitch killed 7,000 people and made 1.5 million people homeless. More recently, in the USA, Hurricane Sandy had an economic cost of over $68 billion. Estimates of damage from 2017's Hurricane Harvey range from $150 to $180 billion. Despite the danger, the desire to build right on the coast continues unabated. It's a problem that focuses the attention of physical oceanographers at the University of Miami in Florida. A major Category 5 hurricane may have storm waves well over 30 feet high. When storm surge is added to the equation, the result can be devastating. Here, they can safely study the potential impact of waves on man-made structures using models. And as sea level rises, the damage from future storms could be even more catastrophic.
Is a parameter that is now well measured throughout the world, and it is now very clear from those measurements that sea level has increased on average by almost 20 centimeters since the beginning of the 20th century. And it's only the beginning, because the projections for the end of this century show a possible increase in sea level that's between 30 centimeter, 1 foot, and 1 meter, more than 3 feet. Potentially big changes for millions of people living close to coasts.
With coastal populations increasing, engineers and scientists are looking for new ways to protect shoreline properties.
Well, protective action can be seen in 2 categories. One is adaptation, is kind of weatherproofing, having better building codes so that when intense wind or rain comes, those infrastructures can resist better.
In 1992, Category 5 Hurricane Andrew smashed into Florida, an event that was to change the standards of an entire industry. Today, hurricane safety building codes are enforced by inspectors like Eugenio Santiago.
I think Andrew taught us a very, very valuable lesson. We need to make sure that things are built the right way, both from the design point of view and from the construction point of view.
And just what dangers are those changed regulations seeking to prevent?
Well, the worst damage is what we call the envelope. The envelope is what protects the perimeter of the building. It's either walls or glass. And if one of those two fails, then wind gets inside and just destroys the building. You blow on a balloon, and you blow it long enough, the balloon explodes. That's what happens to a house.
This damage was inflicted by a Category 1 storm. With global warming, we are threatened by far worse. Some scientists attempt to limit loss of life and property destruction by working on both protection and prediction. Equipped with high-tech specialized instrumentation, Florida University's hurricane research team ventures into the storm's heart with forest masters at its helm.
So for many of you, this will be your first time traveling into a hurricane. I need you to listen closely. We're going to push hard to intercept the storm. It's absolutely imperative that you follow my instructions, stay vigilant, and let me know if there's anything that's going to prevent us from collecting data or creates an unsafe situation. So weather deteriorations, they're going to deteriorate quickly. Just stay alert. Let's get to work. Deploying on such short notice creates a lot of logistical issues. We have to think about fuel, where we're going to set up, where we're going to lodge, what's our evacuation strategy. We have to make all decisions on the fly. Generally, as we're driving into the storm, most of these decisions get made. Once we leave, we drive directly into the storm. Using aerial imagery and local knowledge of the area, we deploy the equipment in sites that are expected to be in the worst winds.
As Hurricane Isaac threatened landfall over the Florida Keys, Forrest and his team raced to get the instrumentation in the path of the eye.
Data are scarce in tropical cyclones worldwide. If we look specifically at the United States, there have been significant historical moments where we've had a major event and we've had very little data to rely upon post-event. So even today, when a storm happens, it's very unlikely that we'll have intact wind speed records from the fixed weather stations that are out there. So we have this specialized mesonet, which is essentially a collection of weather stations that we deploy in the path of the landfalling hurricane. And this gives us the high fidelity information we need to reconstruct what happens at landfall. We work using portable instrumented towers that have specialized instruments that characterize the speed of the wind and also the diameter of the rain particles. The importance of this technology is it allows us to reconstruct the rain intensity, which we can compare directly to the wind speed at that particular site. And so for the first time, we're able to look at how do the winds and rain evolve as rain bands and other features move through the impacted area.
The storm barely brushed the Keys before heading across the Gulf towards Louisiana. With over 1,000 miles to drive, Forrest and his team were racing against the clock to catch up.
We have very few chances to conduct these experiments. We have to seek out the most heavily impacted areas, which always brings us in the vicinity of the eye wall. We're looking for the radius to maximum winds, and that's the distance from the center fix where we expect the most severe winds to happen. Hurricane Isaac is a very unusual storm. It intensified right before landfall. Now it's moving through, and at the speed that it's moving, it's going to take some time before it leaves the area. Isaac presents a fantastic opportunity for the research community. There are literally dozens of assets spread across the state right now collecting data. Many of these are co-located, so we'll be able to go back, look at what's going on aloft, and be able to compare to what's going on below. This is a real first for our field.
Teams of scientists gather precise, high-resolution wind, rain, and Doppler radar data directly under the eye of Isaac. Analysis of such events will give greater understanding of the small-scale features that create the structure of the hurricane's eye.
We're trying to reduce the loss of life and property during extreme wind events. And in order to do that, we have to have a very clear picture of the wind and wind-driven rain environment. The work we're doing is filling in a critical gap. We're taking measurements in the building stock, amongst the buildings in hurricanes. This is where the damage happens. These data are used by many disciplines outside of engineering, including meteorology, hydrology, and other fields. For example, the type of wind-driven rain data we're collecting can be compared directly against the predictive models that are used to predict the rainfall deposition in an area using radar information. Ultimately, we are strengthening the knowledge base by going out and collecting information that really simply doesn't exist. And over time, through more and more storms, we'll build a large database that we can turn back to hopefully develop better predictive models.
When he's not chasing storms in the field, Forrest recreates hurricanes in his lab in order to test building materials.
So we built a machine to replicate hurricane conditions in a controlled setting. We can generate up to 230-mile-per-hour winds, and this creates significant pressures on the roof coverings. And in turn, that allows us to find exactly when the failure threshold is expected to occur. Let's bring it up. Where we can carefully control the wind speed to replicate what happens on an actual roof.
The aim is to design roofing materials that can withstand the wind speed of the most severe hurricanes. In 2012, Hurricane Sandy tore apart hundreds of homes and businesses on the New Jersey coast.
This is the back of our safari ride. As you can see, the water came out from underneath the boardwalk and took up all the piling, all the boardwalk ramps, and did some pretty good damage into this ride and the pier that's connected to it.
10 to 15 seconds, it'd be gone. It was like going about 50 miles an hour heading south. Something I've never seen before, and then I realized that there was some real destruction going on because I'm seeing almost whole sides of houses going past my house in the ocean.
What I saw was 3 foot of ocean water coming down both sides of the street. After looking at the waves for 10 minutes, I realized that all the oceanfront homes were going to get punched out.
You know, there wasn't very much rain. The rain was very light, but the wind was absolutely incredible. You know, I've never, ever, even with all the other hurricanes that have, you know, come through, Irene, etc., I'd never seen the ocean quite like that.
Events just a year later, in 2013, set a terrible precedent. When this monster storm made landfall, it completely destroyed the city of Tacloban in the Philippines. 45-foot waves and 200 miles per hour winds left at least 6,000 dead. It was Category 5 Super Typhoon Haiyan. Strongest storm landfall yet endured by mankind. Are these tragic events of the recent past a glimpse of our future?
My name is Sharon Cox. I live here in Harbor Cove in Northport. I expect a hurricane Category 4 to approach this area sometime tomorrow, which is Sunday. Middle of the afternoon. It'll be a serious hurricane, and it is going to do a lot of devastation.
Summer 2017 saw a full-on assault from Mother Nature, with major hurricanes hitting one after another. Hurricane Harvey made landfall in Texas, causing massive destruction and serious flooding. As it stalled over the state, vast amounts of rain fell, making it the wettest storm in U.S. history. Just 2 weeks later, Hurricane Irma hit Florida as a Category 4 storm, having swept through the Caribbean. Ten days later, Hurricane Maria engulfed Puerto Rico, the strongest storm to hit the island since 1928. Lying directly in the path of the storm, the entire island lost electricity, water, and all communications, leaving the inhabitants in a humanitarian crisis. The 2017 hurricane season is set to be the costliest ever on record. It may be the beginning of a frightening new phase of superstorms. In September 2017 alone, there were 6 separate Category 5 landfalls. Before that, just 18 such landfalls had occurred in the previous 165 years. The strongest hurricanes require an exceptionally warm ocean to intensify, and with record high ocean temperatures in 2017, conditions were ripe for Category 5 storms. Scientists predict such superstorms will become more common worldwide, including in the tropical Atlantic and Caribbean. How seriously should we take these predictions?
We can't make a reliable intensity forecast out to 5 days, so I'm not sure how accurate that it's going to be out, 100 years.
What is clear is that the sea level increase will render the effects of hurricanes and tropical storms in general stronger and more damaging.
No matter how many hurricanes we have in the future, if there are more hurricanes or fewer hurricanes or the same number of hurricanes, whatever hurricanes we have are likely to cause more damage because of the gradual sea level rise.
In an uncertain future, there are certainties. Natural habitats are weakening. Urban coastal development is increasing, and sea levels are rising. Hurricanes are part of nature, but they also present us with environmental, economic, and even moral problems. In the future, they may be more powerful and inflict greater change than even those of today. We cannot stop them. The best we can do is improve prediction and protection, and perhaps learn to adapt to them in our rapidly changing world. In 2017, Hurricane Maria wiped out Puerto Rico's forests once again. Only time will tell if they will regenerate as they have done in the past. Even species that have lived for millions of years have no guarantee of survival. Hurricanes are agents of destruction and of rejuvenation in equal measure. But with many ecosystems weakened, the superstorms of the future may prove too powerful for our fragile Earth. As our weather systems, our climate, and our world change, we can only hope that the balance of destruction and rejuvenation remains stable.